I hope the lectures are getting up in time. Usually I just sit outside here and, process it and upload it right then. So I hope they're there. Then the other stuff we should perhaps touch on is like, are there any issues with the problem sets or anything like that? Or the homeworks are all straightforward and when they're due and everything? No process problems. Okay, great. I will get another homework out by the end of the day today, like by midnight. Okay. I'm still trying to figure out what's the best homework to do for this part and the image quality, the part that we did the other day. There's so many good things to do. But what I think we might do is create so that you can simulate a data set that would be obtained perhaps in evaluating image quality, and then apply some of these metrics to it, and then start tweaking the data and see how the metrics change, right? See whether or not the metrics for evaluating the quality of the study actually makes sense. So kind of a more practical thing. Okay, let me move this. So to begin with today, we're going to talk about segmentation. And the chapters, they're not really chapters in the book. There's two or three papers that will appear, and I'll give you the links to the papers. They're freely available with a PMID number, etc. Where I've drawn some of this stuff from. The first one is this paper by Taha in BMC Medical Imaging, in which this is a sort of, casts a wide net and tries to gather up all of the metrics that are computed to evaluate the success of segmenting different tissues and images. And you can see there's a fairly extensive list right down here. We've looked at some of them already. The true positive rate, true negative, false positive, false negative. So you're very familiar with these, and you're familiar with the ROC curve derived from those, right? Which is what we did last time. Are there any questions about that, by the way? Or it's all pretty clear? Okay, great. And then there are all of these other indices, which when you go to publish a paper and you say, I have a new method of imaging cancer in the lung, right? And I have a high detection sensitivity, and you don't have ground truth. Well, maybe the reviewers come back and say, well, you have to at least show that for an observer, for a set of observers, you get consistent results, right? And that could be the intra-class correlation, right? It's just at least we know that you have consistent results as opposed to results that are going all over the place for the, say, the size of a lung tumor. So we'll look at some of these. We're not going to look at all of them. Basically, I thought we would use this paper, but essentially this is just a list of the techniques and then a formula, and very little explanation of how that formula is derived or what assumptions go into that formula. All of this stuff is basically statistics. It falls into the realm of statistics. If there's something, if you are going to go into a career in research, you basically should spend a considerable time learning some statistics, because you can paint yourself into a corner in an experiment pretty quickly by ignoring some of the fundamental tenets of performing a trial in which each sample coming in is, say, independent, and you know what the noise distribution of those samples are coming in, right? If that's not taken into account, sometimes you find results that are pure artifact of just the way you selected the samples. So we'll look, this paper is, I think it's on the site, or a link is on the site. And it gives a nice sort of laundry list of these techniques. So what we can start with to begin with is we'll just run a simulation, or I'll just run through how segmentation can go for one application, right? And running through this example, we'll see, where variability can enter, in making in doing the analysis. And so our task in this little example that I'm going to run will be a task that we've done many hundreds of times in our research in the lab, which is what is the volume of blood contained inside the left ventricle, right, from a medical image. So this could be an MR image, it could be a nuclear medicine image, it could be a CT scan, right? And the question is, all of the pixels or voxels in this volume painted red here, we have declared that they are blood in the left ventricle. So they've been set into that class, right? All of the pixels that are not red in that picture have been set into the complement, which is the not blood class. Okay, so it's a very simple bifurcation of pixels. And when we're making a decision, so remember when we looked at the statistics in ROC curves, our decision was, is this patient abnormal or is this patient normal? Here, the decision is very similar, is this voxel blood? Is it not blood, right? So that form of statistics is pretty simple. So I'm gonna actually jump out of PowerPoint and go into a software package here. This is called ITK Snap. And oh, I'm already in ITK Snap. Oh, that's good. But it doesn't seem to be. Sorry. Can't get out of that. Shoot that down here. Okay, there we go. Okay, this must be where I left it when I took that picture. So let's go find some data. Let's do this. I'm going to quit it, and I'm not going to save that. And we'll start it up again. Okay. So we're going to look at this software, and we'll analyze some images. So each one of these is a previously analyzed volume, right? So let me take a look at this one. So I'll upload this volume into the software, and you can move around inside this volume by just taking the cursor and centering it. Okay, so we have essentially a axial view of the heart here. This is a sagittal view, which means we're looking from the left through to the right of the patient, and so their chest is up here, their chest is here, their back is here, as you can see, the spine, the aorta. Their left arm is over here, their right arm is over here, so we're looking from their feet up in this view. And then if we look from above the patient and look down upon them through their chest, right, that's called a coronal view, which is here. And this is their left arm on this side, their right arm on this side, their head would be up here. So I have these three orthogonal views, and our job is going to be select out all of the pixels that are blood and count them, right? And once we've counted them, we can determine what the volume is inside the left ventricle. And that volume changes over time. And so you want to be able to make accurate measurements of that over time and plot a curve that is volume over time of the left ventricle. It's a pretty simple thing. The difficulty in doing segmentation, and this is why deep learning, everybody's so excited about deep learning, because it's the biggest thing, or it's made the largest strides forward in doing automatic segmentation than we've seen in 25 years, right? So I've been doing segmentation of MR and CT and everything for a long time, since probably the late 80s, right? And there is a stack of papers on fantastic segmentation methods that people have obtained PhDs inventing. It goes up to the ceiling, right? If you stacked all these together and printed them, go up to the ceiling. And the unfortunate truth is that none of them actually work 100% of the time. They work 90% of the time. Problem is, with 90% of the time, you have to go through all of your data and look for the 10 that are wrong, and then go in and fix them. And so it becomes very expensive from just a cost of human interaction, right? So if you could train something that came back and got, 99% of the time, you just use the wrong one, and it's not going to change your results that much, right? So, so here, I mean, the obvious thing here, this is a scalar image in the sense that there's one pixel value or one voxel value per space. In magnetic resonance, you could have 3 pixel values, right? You could have a T1 weighted scan, T2 weighted scan, proton density weighted scan, pre and post contrast scan, all of these things, right? So each voxel could actually be a vector. It could have 4 numbers associated with it. And as we saw with nuclear medicine, often what's done with nuclear medicine is you merge essentially the SPECT image, which is sort of the intensity of the radiation, with the CT image. You make one picture, right? And so that also can be a vector. If we look through here, there's some interesting stuff. So one way, we can just go up and down axially. So this is the top of the heart. This is where the aorta comes out of the heart at the top towards the patient's head. And then we move down into the heart. Here's the left ventricle. This is the right ventricle. Obviously, the contrast that was injected into the patient has now departed the right ventricle. It comes in there first, right? You put the line into a decubital vein or something like that, and it comes up through the superior vena cava into the right ventricle. So the right ventricle lights up first, then it goes to the lungs, and it comes back into the heart, into the left atrium, and drops into the left ventricle. And that's the phase that we're taking this image. So you have to get that delay right. And when you want to take your picture, you don't want your contrast somewhere else. And if you wait too long, if you wait a minute, all the contrast is spread out all over. And so the contrast goes down. Does anybody have a guess what this is? These very bright dots. So this is the right ventricle of the patient here, left ventricle, so myocardium here, aorta. Got any get? Yeah. Yeah, so we can see how they move, right, in space as we go up and down. There's a hint. Well, these are metallic leads inside the patient's heart. So they're used to pace the heart. So many patients have pacemakers. So if you have a malady called, say, bradycardia, and that is your heart just beats too slowly and it won't beat fast enough, and you're tired all the time, like when you walk up the stairs, they'll put in a little machine, and it's a pacemaker. It goes in a pocket right here. They just make an incision in the dermis and they slip it into a pocket. And they cut down into your superior vena cava, and they wind that thing into the heart, and then they maneuver it around under X-ray, and they plug it into usually the apex of your right ventricle. You do it on the RV side because that's low pressure side, so you don't have blood squirting all over the place when you're trying to get this done. And it'll have a little tine on the end, like a little anchor, and it plugs into the tissue, and then you pull on it and go, up, it's in. Sew them up, and then start this thing going. It's just like it gives an electric pulse to the heart and paces the heart, right? Obviously, it causes issues in medical imaging, specifically in MR. These pacing leads at one time were very, you could induce currents in them when you're in an MR scanner. By all of the RF radiation, it would induce currents and they'd heat up. Manufacturers now make pacing devices that they claim are completely MR compatible. So you get rid of all the ferromagnetic material you can, right? And you put in filters such that you don't generate big currents in the leads. But in CT, doesn't matter, right? Because they're X-rays, doesn't matter. They just show up as really high attenuators because metal attenuates X-rays very well. And nuclear medicine doesn't matter. Nobody cares. They're there. Right? So, we can look up and down and say, okay, we're going to measure all of these pixels and get the left ventricular volume, right? So we start this process by saying, okay, we're going to do a 3D segmentation, and it gives us this window, and we center ourselves up in the ventricle from all of these different views. So this is head to foot level. We'll go in the head, anterior, posterior level. We'll try and get ourselves focused in the middle. This is still well away from any border. This isn't bad. Focus it here. And one of the most successful ways of doing a segmentation like this is if you have a ball inside the left ventricle that you have declared is blood, right? And so it's a sphere in there. And then you let the algorithm push the sphere outwards, and it just continuously adds pixels on the outer border until it hits something that there's a signal, an imaging signal that says, no, I'm not blood anymore because I've gone down like this. And so it can use both the gradient, the signal gradient, the size of the signal gradient as a signal to stop, or just the absolute value there to stop. And these are one of those techniques that's been evolving over decades, right? And when you're building your sphere that now is going to conform to the shape of the left ventricle, you can obviously add mathematical terms that cause that object to either be smooth or allow it to be very rough. And so, go ahead.
I was going to say, so is the threshold value set on a patient-per-patient basis, like the algorithm calculates what things would be a necessary kind of dip in signal, because everyone attenuates differently, so you can't maybe that would be slightly fairer number. But
Absolutely, absolutely, and we'll see how we're going to set that for this patient, because if you don't do that, you're off in space, right? So the variability of the intensity here can be quite high from patient to patient because the injection timing can be a little off, right? So a factor of 2 is not abnormal to see here. So in one patient, the Hounsfield unit in here might be 600, and the next it's 300. In both, in the myocardium, it's maybe 100, right? So yes, and you can make the algorithm do that for you, right? Make those statistical measurements for you and then adjust its threshold as to what it thinks is the boundary between blood. There's a technique called Otsu's method, which we can actually look at it on a scan. But if you did a region of interest that included the myocardium here and the blood pool, so that's thousands and thousands of pixels, right? And we include both those tissues in that, just in a single slice. And you plot a histogram, right? You're going to see 2 peaks in that histogram. You'll see a bunch of signal that's clustered around the mean value of myocardium, and it will have a distribution around that mean. And then you'll have a mean up at the contrast agent, it will have a distribution. Take those 2, and you put your threshold right where you have the highest. You guys get to choose, right? So do you want sensitivity plus specificity to max at that point? You know, you can actually measure it. And so when you have that histogram, you just usually where the two histograms come together and they're a minimum, you just put a threshold right there. Okay? And that we do that all the time. It's called Otsu's method. And when you say you've done that, you can guarantee that you're going to have a reproducible number, right? Because if you swing that thing around, you might get a slightly bigger volume and a slightly smaller volume. But if you declare this is the way we're going to set the threshold, at least it's reproducible. If 5 people do it, you can't get the same darn number because they're all going to get that same Otsu's threshold, right? So that's an important point. Thanks for bringing that up. To that end, we can see here, here's a histogram of the pixel values in this image of all of them, right? Not just the heart, but the whole field of view. 0 is water in CT, right? Minus 1,000 is air. So this would be minus 1,000 in the lung or minus 900 or something, minus 1,000 out here in air. And then we have some very bright pixels up here, close to 1,000. That's probably these guys, right? There's some very bright pixels out there. And then in here is where all our decision occurs between blood and myocardium, right? The histogram isn't terrific because we haven't windowed down our volume of interest to just include the heart. That's time consuming and hard to do, actually, with it automatically. It's hard to do. It's now, again, with deep learning, people have shown that a number of networks have been created where it will just draw a circle that's roughly the heart. And so at least now everything else is gone, right? You haven't segmented the myocardium or the blood yet, but at least you're sort of got the heart, you know, it's isolated. Those are pretty successful. So we can look at this picture here in context with this histogram, okay? And what this is saying is everybody, all the pixels above this threshold here that are inside this window, I'll label them white on this, like, and the rest blue, right? And there, so this is a mixture of the grayscale of the image and that decision boundary there. And we can do things like change the lower threshold, right? So as I move this line to include more pixels, obviously more of the pixels are contained in the analysis. If I bring the threshold up, I can look at the picture and say, you know, that's about what I believe is the boundary of this myocardium. For this threshold, it doesn't really matter that we eliminate all these pixels up here. It might for these guys. So let's try that. Let's, in the upper threshold, we can bring it down. Whoops, I think I really screwed it up now. I think I inverted something. Let's try lower only. There we go. Two-sided. There we go. Yep.
So on the threshold filter, it's not like a straight line up. It's got like a slope.
Mm-hmm.
Does that mean that with those pictures, it's only kind of showing them, or it's only showing some of them, or is
This is, I think you can identify this as kind of probability of inclusion in the class. So here I got a 50% chance I'm blood. And so when the algorithm runs into a pixel of that value, it carries with it that amount of weight that should I include or not include, right? Mm-hmm. And then if everything around it is 25% and it's 50%, it might just throw it out, right? Say, okay, yeah. Say, nope, I'm not moving forward into this space, right? So again, this looks okay. I don't know if we've eliminated the centers of these leads, which is kind of interesting, right? The centers are super bright. And one of the things that happens, and we'll see this on the next example, is that if the artifact from the lead bleeds into this area here or volume, then you got a big problem, right? And we'll take a look at that. This one's pretty easy though. Okay, so let's leave that the way it is. Everybody happy with that? In terms of our, and then there's smoothness of the surface. Let's just make it, oh, that's the smoothness of the threshold here, right? So here we're including a lot of points that are on the sort of border. And here it's just almost a discrete decision boundary. So let's make the discrete decision boundary. That's kind of simpler. So one of the issues or one of the features of a segmentation algorithm looks like this is that you can see there are regions here that are still below the threshold for inclusion. But because they're so overwhelmed by their neighbors, they're just going to get marched across, right? And they'll say, yep, that's some kind of noise process. I'm just going to include you and not make a little pocket. Let's go back up here. Okay. All right. So we'll go next. And so now what we can do is we can put a starting sphere. Okay. And so we'll just add a bubble here. And what we're saying is everything inside that bubble we know is blood, and this is the cross section of sampling through that sphere, right? And we can, in fact, if you want to do a lot of work, you can come down here, say, let's move that up there. You can put another one, right? And so you could seed, these are the seeds for the growth of the segmentation, and you can, if you're concerned that it's not going to grow into the apex quickly enough, you could go down to the apex and put some seeds down there so that it grows there more quickly. So now we'll say next. Okay, and so there's our seeds. If we update this, we should see there's our seeds right here, right? And I forget how you zoom. Is it control? Yeah. Okay, so far, this is our left ventricle, right? And now what we can do is, let's set the step size. Well, let's just do it. I'm just going to start the process, and it's going to make decisions. This is called a snake's algorithm, where it has some structure and it moves it out into a smooth structure and asks the question, should I keep moving or should I stay here? So you just start that going. Okay, so it seems to have moved all the way to this border, which is great, and stopped. It seems to have decided that's not part of the blood and it just didn't bowl over it. Okay, we'll update this, and this is what it looks like so far. And so it's just a bigger round sphere. What I can do though is, let me put this up. I think we can set this to continuous update, which is more fun. Okay. So let's turn it on for a while. You can see it now is finding the borders, right? And if we rotate it around, we can see it's not only doing that, but it's also finding the valve. This is the aortic valve. Here it's growing up out of the heart, out of the left ventricle, up into the aortic outflow tract. This is not part of the left ventricle. This is part of the left atrium, right? So mitral valves here just like blew right through the mitral valve and went into the left atrium. You can probably see that in one of these. There you go. So here's the aorta. It's going to continue to grow through the aorta, and then on the left atrium, Probably the valve plane is here and it's just going up into the left atrium, which, right? So does this look like a left ventricle yet? Nope. Still has to grow into the apex, right? So it's going to have something down here. And then while this is growing, so are these. You just go more iterations and it just extends this volume. You see, these have stopped moving. They've hit a surface that they just can't get through. The gradient's too high. It's okay, we're done. So what I usually do is I just let it grow for quite some time until all of this does not move anymore, okay? I don't really care about the stuff out there. So say finish, and there it is. That's our segmentation thus far. Now, unfortunately, to measure the volume of the left ventricle, we still have a job left, right? If we just count up these pixels, obviously we're counting pixels in the aortic outflow tract and we're counting pixels in the left atrium. So that's going to give us an erroneous value, and they're completely dependent on when we stopped, right? So the number would not be reproducible. And this is where the finesse comes in with something like this. And that's like, how do I now remove the stuff that is not left ventricle and remove it the same way for every observer, right? And that's not easy to do, right? So if I think we can zoom this guy, if I just want this one, okay? So that's our 3D volume. You can see that the surface of the inside wall of the heart is very well rendered or sampled, right? Because the surface of the heart is kind of rough. It has what are called trabeculi. And so the blood is like crawled into those trabeculi. And when we measure the volume, it isn't just like a smooth, interpolated cubic spline. It's actually all the blood that's inside those little intricate spaces, right? So that's good. And if we grew this with that Otsu's method, it would grow to the same thing every time, right? Yeah?
So if you don't see the need to still use that just like a slow rate, start.
If you don't, I don't understand what you
So
mean.
down
Don't.
here, originally you put the 2 seed levels in.
Yep.
And then like you said, it goes outward from that.
Yep.
You don't seed it.
Oh, seed it. Oh,
That's
I
what I'm
see.
saying, did the algorithm then just have to take more time to
Mhm.
towards like for boundaries?
Yeah. Well, with this algorithm, you always require a seed, and it's assumed that the seed is inside the volume you're trying to segment, right? And so it grows out radially, and it grows out with a certain step size that is based on the smoothness of the surface and the gradient in front of it, right? So you always have to put a seed. We could have put a tiny seed, and it just would have taken a long time to grow, right? It would have gone to the same place though.
So, well, in terms of, so as far as you can offer your set seed, or you're saying that they'll have also set seed?
Yeah, you could imagine a neural net could set a seed based on the picture, right? So if you gave it 1,000 hearts and you put a seed in 1,000, you trained it to put it there, it would do pretty well, right? Because the features in the images are fairly reproducible. So I think a neural net would just like, yeah, I'm gonna put it there. There are neural nets that have been written to, for example, detect this point. It's called the apex, right? And so neural nets for MR is way ahead in having large databases to train networks. But now you can just hand an MR picture to one of these nets and it'll tell you where this point is. It'll tell you where this point is, like the middle of the outflow tract. It'll tell you where the middle of the mitral valve is, all that kind of stuff. So the geometric locations, it'll just make them. And they're pretty good, right? It would be handy to have that right now, right? It would be handy to have a point here that we could just say, based on that point, And based on, say, the moment arm of this signal of the aorta, so I'm going to make a vector that goes from the point up the aorta, and then I'll just cut it at the point. So you need a direction. We're going to have to cut this off, right? So now this is where the clever stuff comes in. Well, how do we cut that off? What do we do? Should the stuff below the aortic valve, this is called the LVOT, left ventricular outflow tract, should we include that in the volume, right? And in 100% of clinical imaging, it is not. And in fact, most ejection fraction, when you look at the volume at end diastole and end systole, most of those computations are done based on data down here that's fit to some simple model from echo, right? They don't have enough features to go up here. So when you do volume measurements with CT and you compare them with echo, they're completely different, right? They're quite different. Because echo, they interpolate a lot. So I'm open for proposals, how to cut off the left atrium and how to cut off the aorta, right? What should we do? How do we do that? The first, I'll take a stab at it. So let's line the ventricle up so that it's up and down like this, right? There seems to be a signal right here, right? And that is where the left ventricle comes up to the mitral valve and pinches in, and then the atrium goes out. So there's like this little pinch there, right? So we could find this in most people, this signal, right? And let's just cut it off there, right? So let's give that a try. I think we take this, little red, we're gonna paint over, I'm gonna clear the label. Draw a line there. This gives you this little arrow, and if I say accept this cut, it will delete everything in the direction of the arrow, right? So we don't want that. We want the opposite way, so we'll flip the arrow. We're going to delete all this junk up here, right? So we accept that, and out it goes. It's gone. So it's, a simple thing, but it leaves us with a situation where from one observer to the next, it's going to change a bit, right? So we're still in the same boat. We still have to worry about, if I give this to 5 people, I'm going to get 5 different answers, right? The same one person might be very consistent, but there's probably some kind of bias between one person and the next person when we do this, right? So, but at this point, you can just write this volume out. If you're really concerned about the LV outflow tract, there's still a little bit of it here, right? This is the septum. The septum's quite smooth, the tissue on the septum. When I look at it this way, I say, well, is that ventricle or LV outflow tract? It's a little bit of the LV outflow tract left. But maybe it just would give us more variability if I also tried to delete that, right? Say I did this, bump, and took that off, right? Now I just have ventricular blood, right? However, I have had to make this cut and this cut, and so I'm at the mercy of my people doing this. This is a real problem. I mean, we have lots of people who have worked in the lab, undergrads who work for like 15 bucks an hour and stuff like that, who do what I just did, but 10,000 times, right? Just there's so many. For a single heart, you might have 20 time frames, 20 of these, and we have 1,000 patients, right? So you can see why automatic segmentation would be a gift in the sense of cost reduction and the possibility to do studies in very large trials, right? If you say, oh, I have 10,000 CTs, we really want to analyze the following, unless you have an automated segmentation, you're kind of screwed, right? It's really, really tough, right? So that's why this is a very important problem, and that's why everyone's really excited about writing networks that get this right, okay? So you just write this out, count up all these voxels, and that's your volume. This will, if we look forward and say, well, how would you evaluate whether or not one volume is the same as the next, right? If I have a gold standard or an underlying truth where I had the best person in the world segment this by hand, and this is somebody who's like extraordinarily experienced, and so we trust that person, say, okay, what you say is the truth, you know. And then we perform our algorithm, and we want to ask the question like, how close did it get to the right answer, right? So these are what these evaluations that we'll look at today are going to do. And oftentimes, say for deep learning algorithms, when they iterate and try to get closer to the truth, right, you'll use something like either a Jaccard index or a dice score. And that's basically the intersection of this volume that we just did with the truth. So how many voxels are the same, right? Divided by that number plus the ones we missed, plus the extra ones we put in, right? And so that fraction is called the Jaccard index. And for something like this, you can imagine it's pretty darn close to 1, right? Because most of the voxels are inside here, right? And so you have this thing that is really darn close to 1, and you're looking at oscillations in that to try and push your algorithm towards the truth, right? That's used for both deep learning, like training algorithms, and for evaluating your new method in a paper that doesn't use deep learning, right? They still want to see some kind of index like that that tells you that you're getting close to the truth. And if you don't have the truth, what do you do? Like if an observer exists, or the super experienced observer doesn't exist, what do we do then? Right? Maybe this is data that just is new and there isn't any observer, right, that has done 10,000 of them. Then we're going to look at a thing called the intra-class coefficient, which is, can you at least do this reproducibly? So we'll do 20 patients, 50 patients. We'll have 4 observers and ask the question, do all the observers get at least the same answer? Or is there a lot of variation in the observers? If there is, then it's not a trustworthy metric, right? That's the ICC, or intra-class correlation or coefficient. So let's look at those. So I'll get out of ITK. Any questions about ITK now, or this segmentation? This is just one example of a 5,000 ways of doing segmentation of various things like brain tumors, lung nodules, bone versus banging, blah, blah, blah. So this is just the one we do in the lab a lot. If anybody wants to earn 15 bucks an hour, just as to pay your rent, we have thousands of these you can do. Okay, so I won't save that. All right, so that's the demo. Any question? No questions coming in on the chat box. Okay, great. So intersection over union, or IOU, is sometimes what this is called in machine learning. It's also called the Jaccard index. This is from the Taha paper, the formula for that, and it is just the voxels that we truly, get in the right category, right, divided by the number we get in the right category, plus the voxels that we wrongly put into the category, plus the voxels that we miss, and they weren't segmented that way. And so that is it's a trivial number to compute. This is kind of what it looks like in terms of the intersection divided by the union. of these things. And, you know, it basically, when you publish a paper, oftentimes you give this index, you know, in terms of if you have an underlying gold standard, right? The DICE index is essentially exactly the same, just with a 2 here. And does anybody know what that is? I don't know what the underlying model change is or anything, but obviously it seems to, I guess, weight the true positives more heavily, but it weights them on both on the numerator and denominator. So I don't really understand what that is, but so they're essentially the same thing. I mean, if one has a maximum, the other one's going to have the maximum at the same point, right? If you're modifying something. So that's called the DICE index, if you're ever wondering. So this when we're looking at these performance metrics, and we're saying, well, how close are we getting to, say, the true value or the mean value of the metric from an expert, etc. You can, specifically in those cases, when you have two features, like you have x1 and x2 are two features, and saying, well, what is my distance to the correct value? So if these are all the measurements I've made of those two features in my data set, now I make one measurement here and I make one measurement here. And we evaluate whether or not this one is an outlier or this one is an outlier. If all you use is the Euclidean distance of this measurement to the mean of the group, and this measurement to the mean of the group, you can see you're going to make a mistake, right? In that this measurement is far less probable of occurring than this measurement. For those of you who've done principal component analysis or machine learning with probability density functions, you can fit this sort of elliptical group of data points to a probability density function, which, if you look at its contours, you know, of equal probability, they're going to be ellipses that look like this, right? And then as you move along those contours, the probability of that point occurring diminishes, right? So you can compute a distance called a Mahalanobis distance, Mahalanobis. And essentially what this is a distance computed in a coordinate system where these tendencies of the data have been normalized out, right? And you can do that using the covariance variance matrix of these data. And I'll show you the formula for that. There's a pretty nice quick description of this on YouTube. I put it down here if you want to watch that. And I stole these pictures from that. So so if you look at so the characteristic, you know, eigen vector length or eigenvalue of the covariance matrix in this case, you have a long or a large eigenvalue here and a smaller one here. And this is what you would get from doing principal component analysis on this data. It's like, where is most of the variability? Well, it's along this direction. And then what's orthogonal to that to get the residual variability is along this direction. So it's two-dimensional, you get two of these values. So essentially we're gonna, instead of using Euclidean space in our measurement space, we'll start measuring things in terms of distance along this direction and distance along this direction, right? And algebraically, it's simple to do. You take the inverse of the covariance matrix. So it's kind of like the 1 over the covariance, and just map your points. So we have a mean in the plane, right? So in the example I gave you, there's only 2 dimensions. There's x1 and x2. This works in any dimension, right? And so you have the mean, which is in that example was just a point, a 2D point, and your data point displaced from that. You map those as like a coordinate transformation, right, into the eigen, vector coordinates and measure the distance there. Okay, so you basically come up with a new formula for your distance, right? And that takes care of this covariance in a specific direction. If we have two measurements also, say from two observers, and you ask the question like, how far apart are those measurements? Kind of matters that you make that a normalized distance, right? When you're saying, okay, this observer is sitting over here, the mean of this observer is over here, but you can characterize the variability of the two observers and come up with an average of the scaling of the coordinates in that direction, right? So that when I make a statement of like how far apart is observer 1 from observer 2, say this is tumor size and this is tumor size. We could do two other things. This is like the intensity or temperature of a tumor, and this is its size. And this observer makes these measurements, this observer makes these measurements, and you ask, well, just how close are they? We rescale the coordinates such that this distance here is in that normalized coordinate. Okay, so now we're going to look quickly at the ICC, and this is something that every time you submit a paper and you don't put it in, you think maybe this time they won't ask us to do it. They always come back. The reviewers always come back and say, yep, you have some new measurement of, whether it's size of a nodule in a lung image or something like that. They're going to ask you to give this reproducibility analysis. So it's worth knowing this. This paper, it turned out the Taha paper showed all of these definitions, and we've gone through a few of them. But this paper is really nice. It was written fairly recently, and it goes through the 3 models of the type of data you can have when you're doing this interclass correlation. And so I would recommend looking through this paper, and it has some very nice appendices and everything. So here's the basic state of affairs is you have, say, n subjects, and let's say we have n different volumes we're segmenting, just the way I did that. Okay, so each person, we've got n different people, and we're going to do that process, right, in each one of those people. And I'm going to ask a bunch of observers to repeat that process. So this is where it gets interesting, right? So now I've got K people lined up, and they're all doing this for a list of 20 patients, say. BEN's 20. And then we measure not only, basically the subject 1, observer 1 will give us this result, observer 2 gives us this result, and we can get a mean value of, say, volume in subject 1, the LV volume in subject 1. We can get the mean value of these, right, over all those observers. It's pretty straightforward to understand that if there is a lot of scatter around this mean in these values, so if I take the standard error or the variance of these numbers around this mean and it's high, then I don't have a reproducible technique. I have to retrain my people to do it the right way, right? Or come up with a new technique that has things like the Otsu criterion that sets certain reproducible boundaries, right? So there's that. And I have it in this patient. And I also have it in this patient, this patient, this patient. And so these could be completely different numbers, right? Maybe a factor of 2. I do it again, and I say, what is the variability around that patient? So there's now also, if I look down a column of this data, just for this observer, I'm going to see some variability, right, in their answer or in their values. And it'll be essentially from 2 sources, that variability. One is the fact that these numbers are probably different, right? So if I have 20 patients and they all have different left ventricular volume values, then these numbers will be different. And so there should be variability in these numbers, right? It should be scattered. 2, this person is prone to make noisy measurements, right? If they made a measurement on the same thing every time, if there was another dimension here, and we made them do it 10 times, there would be some noise to that. So the assumption is that this value is plucked from a distribution that has a Gaussian or a noise associated with it. So it's one value plucked from that distribution, right? And the normal, usually you assume that that distribution, you know, has a mean, right, and a Gaussian distribution around the mean. Okay, and so you can characterize it with one sigma value. Right. Yep. Oh, we'll get there. Yeah. You're right. You could expand this table and give other things like the variance here. And then of those variances, you look at their average and stuff like that. We'll see there's a whole bunch of that going on as we get into this, right? That's a great idea, actually. We should make a better table than this one. This is just the raw data and the first set of means, right? Okay, and the concept is there's going to be variance across all of this. And what this interclass correlation is going to tell us is like how much of that variance is actually due to the variance between the observers. Like what fraction is that? And so that's where we're headed. So this is the value taken in the table for each. So I is the basically subject index, like for the patients, number of patients. J is the different observers, right? So I have a matrix of those measurements. I assume that what happens is I have a true mean value for the measurement that, like, it's actual God-given mean value for say that volume. And then I have an addition, like, to that mean over the group that is a displacement, right? So this mu value I can calculate for the whole distribution of these values that I've measured. It's kind of a baseline mean. And then everything that is interesting in xi is a differential from that mean, right? And the reason you write that down is this I didn't understand until I started reading about this stuff, is that you really want all of your variables when you're developing this mathematically to come out of a Gaussian distribution with a zero mean. And so this, we assume, this delta that changes from the mean of everything is drawn from a Gaussian distribution that has zero mean. Okay? That is the difference that's associated with being in a different patient, right? Okay, so that's what RI is. That's why it only has an I here. Then there's noise on top of that. There's basically noise in the measurement and noise caused by the fact that we have different observers. Okay, so this term pools all of that noise together, right? And then the interclass correlation, basically the sigma that's associated with this value is here, right? And it shows up in the denominator. And also this, the sigma associated with this value shows up in the denominator, right? So if the noise associated with one observer to the next is on the same order as this scatter in the data, which is one patient to the next, right? Then this value is going to be not very close to 1, right? So let's say these two are equal, right? Then it's going to be 50.5. And that's not a great number. That tells you this number is pretty high compared to the kind of the dynamic range of the numbers that you want to measure, right? And so that's the simplest model for the interclass correlation is this thing, right? Does everybody get this part? This is the most important concept of it, is just, I think Fisher or some really good, statistician came up with this as to how to derive this and say, yeah, this ratio is a very stable way to measure, how much of the variance is given to you by the different observers and by the noise in those observers. Again, this is all in this publication. So how do you calculate it from, as we saw, we don't have these values, right, from the table. We have the XIJs, right? We have this. So how do we calculate these, right, from these is the question. And that's, the rest of this paper is like, how do you do that? How do you calculate and get to this formula from these values? And it just goes, it's pretty straightforward. It says you take your, remember these guys, SI and MJ, they were the means down along the side. Here, these are the means across a patient. And then these are the means down the column across for one observer, right? And we compute basically the X bar, or the average for the whole thing is here. And then we use SI in this formula. It's subtracted from the whole thing. And I actually think this is a typo. I don't think this should be here because there's no J here, right? So it's just the sum over all those I's as we go down the side of that table, right? And that's the sum of the squares between subjects. And you calculate its mean by dividing by the number of subjects you have, -1, because you used 1 degree of freedom to compute the mean, right? To compute this, okay? So they're all related that way. So there's n-1. So this gives you the mean square between subjects, right? And then the sum of squares within subjects, we have this where we're actually doing the computation over the entire field, right, of of all of the measurements. And then we use these two. So this is the mean square between subjects, the mean square within subjects. You can see now you can show that this thing is actually equal to this value here, which includes our sigma of this R multiplied by number of subjects and the sigma of this. So we just rearrange this algebra, right? This is what we can compute from our tables, these things. And so to make this formula, we just use this, which we can compute all of these from the table. I mean, in any stats package or even in Excel, I think it'll do this for you, right? And in the sense, if you have a table, you say this is what it is, it'll give you 3 different models you can use, right? And it'll give you this ICC coefficient, and it will be a number between 0 and 1. And do we talk about the models? No, I don't. Okay. So one thing that's kind of missing in here is the fact that you can model. There's 3 different models, and this is the most simple. Okay. You can write down a model where you have one other term here, which is the value returned by an observer, right? Such that you have a, say, a CJ here as well. And you say that, well, I'm going to model this so that there is bias. I know there's bias from my observers, right? This model we've done here, we don't know that there's a definitive bias between each observer. We just say it's a random number. There could be a fixed bias, right? There's like observer 1 always is bigger than observer 2. And so you can actually write down another model like this, which includes that fixed bias. And that's in this paper. I'll leave that to you to read. And then you should use that when you know or you look at all your data and you say, you know what, these observers have this characteristic bias. This person always gives me back small ventricles. This person gives me back bigger ventricles. Therefore, let's use that model. And the formula changes a little bit then, and the values are pretty close. So that's the intraclass correlation. We use it all the time because we don't have truth, right? And so the best thing you can do is ask 3 people in the lab to do the analysis and see if it turns up like to be the same number. And you can't let them peek, right? So if they, if they start out by where the other person left off and they see how they did it, it'll bias their results towards being the same as that person, right? So they have to be blinded to what the results came out from the other person. And it's because it's pretty easy to cheat, right? And so, but there's no point. Right? You can make this as good as you want. One of the things that, if we go back to the table, that I kind of find interesting, I think maybe we'll do this as a homework problem, is that how does the dynamic range of the true underlying values affect this? So if I'm measuring something that has any number between 10 to 100, right? So I have large dynamic range from subject to subject compared with my essentially scattering the data across the subject. Like, how does that change the ICC, the actual value? And so if I choose cases, so I choose 100 cases and they all have relatively the same volume, right? So these numbers don't really change that much. And I think my ICC is going to be quite different than if I choose cases that have a broad dynamic range of volumes, right? So that, I think, is worth understanding. It's like when you go in and you tell the journal, okay, we've done this reproducibility analysis. It seems to me it behooves you to pick the dynamic range that you expect to see in your data in order to get the RMS, along here that RMS R, the sigma R, to be a fairly big number. Right? So, but we can look at that and see if that comes to pass or if it's normalized out somehow. Okay, so that's all I'm gonna talk about today. I think next class, next Tuesday, we'll start with PET applications, or applications in cancer and all sorts of things. PET and nuclear medicine, probably in cancer. There is a quiz, and the quiz is going to be, let's go back to the, let's everybody get this, April 28th, okay? We are now the 21st, okay? So the quiz, literally what I'm going to do to put questions in this quiz is go through the videos and see what is it we actually talked about so that I stay on topic. I don't drift off topic, right? And so I'll look at what we've talked about, and the quiz will be just that. It's a quiz where, there'll be multiple choice and true false and all that kind of stuff, right? So it mainly is just to evaluate how much of the lecture material and what we've discussed you've retained, as opposed to, hey, let me see if you can invert this matrix, like do algebra. I don't really care, right? So I don't want to see how good you are as a machine. I'd like to know, are you retaining any of this information, right? So that will be that. We can use the entire class for that. Is that usually that's what every class wants to do? They say, yeah, let's just do the entire class on that. So that would be my proposal. Okay. And if anyone has a different notion about that, then I have a question regarding ICC. Okay, okay, so this is a good question. 40. Okay, so any questions about the quiz or? Yeah.
Is it going to be like online, or do we have to come in here?
Well, that's a really good question. I didn't even think about that. It would be probably easier if you came in here, right? Although, I mean, it's like we got 3, 6, 7 people here, right, out of 24, so not many people come in. Let me get back to you on that. Thank you for bringing that up. It's an excellent question. It was to whether or not we can just do it online. And have you guys done that before? Have you done quizzes online and it goes pretty well? Okay, I've never done one. So is there any, how's it done usually? Okay. Yeah.
So we're gonna get your
Oh, okay. Okay.
Just like you do 4 choices, put it in.
Okay. All right, I'll look that up. Yeah, let's do it. Let's see if we can do it online then. Okay. That way, I mean, there's a lot of people who don't come. So plugged into Canvas. Okay, I'll figure that out. If somebody has done one before that they liked the format of it, like on Canvas, just how it came up, then you can shoot me an email and show me an example or something. I agree the grading would be easier too, and everything's in. So the question is, I have a question regarding the ICC. If the between observer variance is so small, even the error variance is not big, should we find another evaluation to replace ICC? Well, no, I don't think so. I think basically that if the between observer variance is really small, then you have just shown that, the darn thing's reproducible. And so that's okay. And your value of ICC is going to come out very close to 1, and that's fine. The issue there is you know, what do you believe, right? And so when you look at the data, I'm a big proponent of looking at the raw data as opposed to just saying, oh, the ICC is 0.93. You should actually plot the values from each person, you know, and as a little histogram around that value, and just see, like, does this make sense? Does that actual value of the variance in this number make sense? If when you look at it and you say, oh, we're calculating the left ventricular volume, and the variance from person to person is like, you know, like 1/10 of a milliliter or something like that, then you say, well, something's wrong with what we're doing here, because that isn't a realistic number, right? So you look at the data, make sure that that raw number that you believe, the scatter around a mean, is in fact a realistic number, right? And it's not, oh, 1 or 2 voxels were missed. That does, it does make sense. Something there has been automated, right? Such that it's like, yeah.
Now, is there like a value for ICC, kind of like a p value, you know, 8.05, you gotta double check that, it's a lot of hacking.
Yeah.
Is there like a specific, like 9.93, like, if it comes into that value,
Yeah,
like that's like kind of the highest they allow in the paper producing.
That's- there's classes of performance, and usually the boundaries of those classes of performance are sort of like between 0.7 and 0.8, and 0.8 and above is great. And so, but from my perspective, it also depends on the details of the test itself and the ICC itself. So if, again, the dynamic range is really huge, right, in the test, and it's some artificially large in terms of the dynamic range of the values, then maybe your ICC is, you know, a little messed up. So, but there is, when you read any paper on ICC, it will have a little section on what is good, what is excellent, what is outrageously good kind of numbers, right? Okay, great. And I will try and get homework 3 out by midnight tonight. How about that? Okay.
Dr. McWay,